Good morning to everyone. So in today's class, we are going to discuss about power factor meters. Okay, in previous class, we discussed about measurement of power in watt meters. We discussed about Blondel's theorem. We discussed about measurement of power in three-phase four-wire 3 watt meter method. We discussed about measurement of power in 2 watt meter method in star connection, delta connection. We discussed about effect of power factor on wattmeter readings. We discussed about measurement of power through single wattmeter method and its phasor analysis individually. And next we also discussed about three-phase wattmeter construction and analysis of three-phase wattmeter. We discussed about in previous classes. I shared the class presentation, PPT presentation, which we discussed in online classes. We discussed that content in 3 classes and the entire presentation and a textbook scanned copy of ML Sony. I forwarded to your WhatsApp group. Just go through it. In meantime, if you have any queries, just let me know. Whatever it may be the session we are discussing. So in today's class, we will discuss about power factor meters. Even when there is a discussion of power factor meters, you can ask doubts related to the previous content also. Okay, either it may be PMMC instruments, MI instruments, watt meters, measurement of power through watt meters, whatever it may be the topic, whatever it may be the content. Okay, you can post your doubt in the chat box, or you can DM to my WhatsApp, or you can call to me at any time. Don't hesitate yourself. Ask doubts frequently so that the discussion will be complete. Okay, so power factor meters is quite lengthy concept. So we will start with the inception of power factor. We will discuss about the basic analysis of power factor, need of power factor, and next we will discuss about classification of power factor. One second. We will discuss about definition of power factor. We will discuss about various classification of power factor meters. What is the need of power factor meters? So generally power factor meters are classified into 2 types. First one is electrodynamometer type power factor meter, and second one is moving iron type power factor meter. So in again in electrodynamometer type power factor meter, we will discuss about single phase electrodynamometer type power factor meter. So in this concept of single phase electrodynamometer type by wattmeter meter, we will discuss about torque expressions. We will discuss about theoretical analysis of single phase dynamometer type wattmeters. We will discuss about mathematical analysis related to torque equation, and next we will discuss about three phase electrodynamometer type power factor meter. So here also we will discuss about a phasor analysis. Phasor analysis is nothing but a theoretical analysis, but in that we will discuss what is the relation between voltage and current, what is the behavior of power. That entire things we will discuss in a phasor analysis. And next, if time permits, in today we will start moving iron type power factor meters. If there is no requirement of time, we will continue in further classes. I think this content of power factor meters is quite lengthy aspects. This will take nearly 2 to 3 classes. This is a continuous session. That means we will discuss around 2 to 3 classes only related to power factor meters. So in today's class, we will discuss the inception, and we will discuss about basic aspects related to power factor. Okay, and classification of power factor meters and individual construction and theoretical analysis and all. In the coming classes, we will discuss about the mathematical analysis and all. Next in our classes, we will discuss about moving iron type and next mathematical analysis. So this is a continuous discussion. So just be regular to these classes so that the concept will be clear. So this concept is an this concept is one of very important related to the competitive exams point of view also. Okay, so even related to when there is a discussion of torque equations, there may be scope for asking so many numerical problems and type of bits in your SSC staff selection commission exams, AP transco gate exam. So electric measurements itself holds a concerned weight in gate exam. So that's why just keep your focus in power factor meters. This is an interesting concept. So first we will start with the inception of power factor. What is meant by power factor? Most of you people are studied about electrical circuit analysis 1 and electrical circuit analysis 2. So in a frequent discussion, either whatever it may be the content, either it may be electrical measurements, either it may be power systems, or it may be in an electrical circuit analysis machines. So we keep on discussing about the constant term for power factor. What is meant by power factor? What does it measures? What does it represents? At what particular instant we will measure this power factor? That means power factor measures The power factor meter, mostly power factor meter measures the power factor in a transmission system at the instant of transmission system. So entire categorical of electrical segment is divided into various stages like generation, transmission, distribution, okay, and unload end or domestic and supplies and all. So here where we measure power factor, okay, with the help of power factor meters, at our discussion we will measure power factor at the transmission segment. So before discussing about the power factor meters, what is meant by power factor? Okay, so power factor is nothing but a cosine of angle between voltage and current. Most of people we keep on discussing the term cosine of angle between voltage and current. That means the angle between voltage and current is represented with the term called technical term called power factor. Okay, power factor. So what does this power factor meter finds? Okay, so power factor meter determines the type of load of line. Okay, so depending upon the analysis of power factor which we observed from the transmission line, okay, so depending upon the range of power factor which we calculated from the transmission line, we can analyze what is the type of load it will be. Okay, either it is maybe a resistive load or it may be high inductive load. What is the type? It may be an industrial load or it may be a domestic load. So depending upon at each individual load classifications will have its own power factor rating. Okay, that means with the help of a power factor meter, when we measure the power factor at a particular transmission line through power factor meter, we can clearly determine or we can clearly calibrate the type of load which we are using with respect to the line. So if we go on through the analysis like this, so if we discuss about the power factor meters and if we discuss about the concept of power factor here at this point of time, so power factor meter main purpose is to provide accuracy. Okay, that means the sufficient data or precision testing, high precision testing is done. Okay, so power factor meter is mostly like watt meters. Okay, we already discussed in our previous discussion about a lengthy discussion of watt meters. Watt meters circuit construction consisting of a current coil which is connected in series to the line, which is called as current element, and pressure coil is also called as moving coil, which is connected in parallel to the line, which is called as voltage element in that all. So mostly these power factor meters which we are discussing are like watt meters having a current circuit and voltage circuit. So we're having the discussion of current circuit and we're also having the discussion of voltage circuit. So here the current coil will carry the current in the circuit. So you are carrying current in the current circuit. The main objective is to measure power factor. Okay, the main purpose is to measure power factor, but here current coil carries the current to measure power factor, but here the voltage circuit is splitted into two parallel paths. Okay, we will see in further the discussion. So just go with the analysis. The voltage circuit is splitted into 2 points. So one is an inductive circuit, and two parallel voltage circuit or voltage element is splitted into two parallel paths. One is an inductive circuit and another one is a non-inductive circuit. Okay, so the deflection of the instrument here, the main deflection or the torque of the instrument depends upon the phase difference between main currents and the phase difference between voltage currents of the existing meter. That means here the main purpose of power factor meter is to measure the existing power factor on a transmission line, the existing power factor on a transmission line. Okay, that is the main objective. So the power factor is nothing but a combination of voltage and current. So if we see the classification, of power factor meters. Power factor meters are generally classified into two types. The power factor meters are generally classified into two types. One is single phase electrodynamometer type power factor meters, and second one is a moving iron type power factor meters. So again, electrodynamometer type power factor meter is also classified into two types. One is single phase electrodynamometer type power factor meter, and additional one is three phase electrodynamometer type power factor meter. Okay, and again moving iron type meter is again classified into various types, that is rotating iron type rotating iron type power factor meter, rotating iron magnetic field type power factor meter, and the number of alternating fields power factor meter. So these are various classifications of power factor meters. There are two types. One is electrodynamometer type power factor meter, single phase electrodynamometer type power factor meter, three phase electrodynamometer type power factor meter, and moving iron is also again classified into two types. So if we discuss in the continuous perspective here, so first classification which we are going to discuss, that is single phase electrodynamometer type power factor meter. Okay, single phase electrodynamometer type power factor meter. So we will analyze this power factor meter, or we will individually we will discuss this power factor meter with the help of a single phase supply. See, this is a single phase supply which we are talking about. This is a single phase supply, and this is a phase connection we got here, and this is a phase connection, and this is a neutral connection. Single phase 50 hertz supply. Single phase 50 hertz AC supply. Here we have single phase supply. So, and this is nothing but a calibrated scale. See, this is nothing but a calibrated scale. So two ends, minimum end is represented with respect to lead, and a maximum end is represented with respect to lag. And here we had unity power factor. This is unity power factor. This is unity power factor. Here we have the one is nothing but unity power factor. So this is a calibrated scale, and this is nothing but a fixed coil. This part is nothing but a fixed coil. See, fixed coil, current flowing through this fixed coil, and the voltage coil is in the previous discussion of introduction also we said there is single fixed coils are connected, fixed on the moving coil or the pressure coil or potential coil. Okay, fixed coil is called as current element. Fixed coil is current coil. Okay, and the fixed coil is called as current coil, and it is also called as current element. Whereas moving coil is called as pressure coil or potential coil or voltage element. See, the moving coil is split into two parts. See, one is represented as scale A, and one is represented as scale A, and additional one is second one is represented as scale B. Okay, what we said, one of the moving coil is an inductive element. See, plane B, see here, scale B or plane B, we are calling that as two planes. Okay, two parts of moving coil or two parts of pressure coil or two parts of voltage coil. Voltage coil or two parts of voltage element is represented as, this is called as coil A, and this is called as coil B. Okay, so coil B is represented with respect to an inductive element. This is coil B is inductive circuit, whereas coil A is nothing but a resistive element, where it is a non-inductive resistance. Non-inductive resistance is present here. Here we have an inductive element. High inductive coil is presented with respect to coil B. That's what we said in our theoretical description. That what we said in this theoretical description. So construction of the single phase electrodynamometer wattmeter we analyzed here. Okay, see, so the entire segment of single phase electrodynamometer type power factor meter contains a fixed coil. This fixed coil will act. See, this element, this segmentation is called as fixed coil. Fixed coil will carry current. Fixed coil will carry current. With the help of that current only, we will measure power factor. The help of current only we will measure power factor. How we are going to measure, we will see in our working analysis. First we are discussing about construction. Okay, so and next the potential coil or pressure coil or voltage element is connected in parallel to the supply voltage. See, in parallel to the supply voltage, in parallel to the supply voltage. So the coil, the moving coil is split into two parts. The moving coil is split into two parts. The magnetic field of the coil current, see, the magnetic field of fixed coil current is directly proportional to the current flowing in this particular moving coil. Okay, so the moving coil or the pressure coil is split into two parts. One is coil A and coil B. Okay, both coils are connected together with a jewel bearing. And it is pivoted with respect to a needle. Okay, coil A is nothing but high resistive element, and coil B is nothing but high inductive coil. Okay, both are connected in series with respect to the coil, and at the end we have load, calibrated load. So if you have any doubts with respect to the construction, just let me know in the chat box. I'm going to the next slide. So if we see this is about the construction and analysis. So if we discuss about the working principle, of single phase electrodynamometer type power factor meter. So this is a single phase electrodynamometer power factor meter. Okay, so current through the coil A is in phase with respect to the current. So okay, current flowing through the coil A is represented with respect to I suffix A. Current flowing through the coil B is represented with respect to I suffix B. See here, current is represented here as I suffix A, and current is represented here with respect to I suffix B. Current through the coil A is in phase with respect to the circuit voltage, while current through the coil B is in lags with respect to the voltage at an angle at an angle theta, at an angle theta. Okay, so here the phase displacement between coil A and coil B is represented with respect to 90 degrees. See here, the phase displacement in between coil A and coil B is represented with respect to 90 degrees. The angle between two planes of the coil is equal, the angle between two planes of the coil. So if we represent the angle between two planes, the phase difference is 90 degrees. But what is the angle difference between two planes? If we observe the angle difference between two planes, the angle difference between two planes is represented with respect to an angle called as theta. Okay, theta. The angle between the plane of coils is represented with respect to an angle called as theta. Okay, so the connection to these moving coils are made with respect to gold or silver ligaments, so that the main purpose of making the connections is so that they can be completely flexible, completely flexible. So let us assume, if we go to the working analysis, if we go through the working analysis, so let us assume the current through the coil B lags with respect to the voltage at an angle of 90 degrees. Okay, so the angle between planes is exactly around at an instant of 90 degrees. 90 degrees. So let us say, if we assume the field of two fixed coils, see here, this is a fixed coil, this is one fixed coil, and this is one fixed coil. This parameter, this segmentation is nothing, this segmentation is one fixed coil, and this segmentation is another fixed coil. This segmentation is one fixed coil, and this segmentation is one fixed coil. If the field created, or that means flux created by these two fixed coils is uniform, the direction of the needle is forward. Okay, the direction of the needle is forward. That means the torque of each coil, the torque produced by the each coil, okay, the torque produced by the each coil at a particular current flowing through the coil is maximum. Okay, the current flowing through the coil is maximum. That means the current flowing through the coil is maximum, and the direction flowing is forward, and the direction of the needle is flowing in a forward dimension. The direction of the needle is flowing in a forward dimension. That means the flux is created with respect to the fixed coils. Okay, so in the presence of that flux, in the presence of that flux, in the presence of that flux, the needle will start deflecting. The needle will start deflecting. That means the meter will have two deflecting torques. Okay, one is deflecting torque produced by the coil A, and another one is the deflecting torque produced by the coil B. Okay, so we have to place the windings of the two coils in an opposite direction, such that the pointer will be moved on a particular uniform scale in an equal dimension, in an equal dimension. Okay, so let us summarize the discussion. So here we have two fixed coils, current is flowing through the fixed coil, current is flowing through the fixed coil. This generated a flux, this generated a flux. Okay, current flowing through the moving coil is represented with respect plane A coil is represented as I suffix A. Current flowing through the plane B coil is represented as I suffix B. So the flux or field is created by the fixed coils, and the flux or field created by the fixed coils will deflect this plane A with respect to plane B. Plane A will create a deflection torque with respect to the flux created by the fixed coil. Plane B will create a deflection torque with respect to the flux created by the ఫిక్స్డ్ కాయిల్. వాట్ విల్ హ్యాపెన్, ఏం జరుగుతుందండి, ఫిక్స్డ్ కాయిల్ అనేది ఒక ఫ్లక్స్ క్రియేట్ చేస్తుందండి. ఫిక్స్డ్ కాయిల్ క్రియేట్ చేసిన ఫ్లక్స్ ప్రెజెన్స్లో ఈ ప్లేన్ ఏ అనేది ఒక డిఫ్లెక్షన్ టార్క్ని క్రియేట్ చేస్తుంది, ప్లేన్ బి అనేది ఒక డిఫ్లెక్షన్ టార్క్ని క్రియేట్ చేస్తుంది. బోత్ విల్ అరేంజ్ ఇన్ అన్ ఆపోజిట్ డైరెక్షన్ అండి, both will arrange in an opposite direction. So we have to make this windings on plane A and windings on plane B in an opposite direction, such that the scale will be deflected on a particular calibrated scale in an equal distributed manner. Okay, is it clear? I think the operation is clear. If you have any queries, just post your doubt in the chat. Is it clear? Okay, అర్థమైందండి. So if we observe the torque expression, if we analyze the torque expression, already we said in the previous discussion, the deflection torque is created with respect to there is a deflection torque created with respect to scale A. Okay, and again there is a deflection torque created with respect to scale B. Both are in opposite dimension, both are in opposite direction. Let us assume the deflection torque created by scale A. What is the deflection torque created by scale A? deflection torque created by scale A, T suffix A is equal to constant K, spring constant K, that is into voltage into current into M. M is nothing but mutual inductance. Mutual inductance between two coils. M is nothing but mutual inductance between two coils. Okay, and the deflection torque acted on coil B. M is nothing but deflection torque experienced between two coils. Where theta, what is meant by theta? So if we see the term, what is theta? Theta is nothing but plane of reference, plane of reference between angle A and angle plane A and plane B. Sorry. Theta is nothing but angular difference or the plane of reference between plane A and plane B. Phi is nothing but phase difference between plane A and plane B. Okay, so this is nothing but the torque experienced with respect to coil A. If we observe the deflection torque produced by coil B, okay, what is the nature of deflection torque produced by coil A and coil B? Coil B will produce a deflection torque which is in opposite direction to coil A. That's what we said. So coil A deflection torque is this one, and in opposite dimension it will create a counter torque, counter deflection torque, that is equal to deflection constant Ki. So M is here in a normal manner here. So here in an opposite direction we created maximum value of mutual inductance. So here the cos phi, power factor is cos phi, here it is cos of 90 minus 5. So cos of 90 minus 5 is in opposite direction, is an opposite direction to cos phi. Okay, and sin theta, sin of 90 plus theta is an opposite direction to sin theta. Okay, so that is equal to I suffix b is equal to k v m max into cos phi into sin theta, cos phi into sin theta. That means here the deflection torque is deflection torque produced by the coil A is in anti-clockwise direction, and the deflection torque produced by the coil B is in clockwise direction. Okay, so the value of maximum mutual inductance, if we observe the behavior of maximum mutual inductance, is same in between two equations. Okay, is same in between two equations. If we equalize both of them, that means the deflection torque created by coil A is equal to the deflection torque created by the coil B. At this type of inception, at this type of discussion, what will happen? So the fixed coils, will is deflected on a uniform scale. Okay, and the direction of the scale is also is happened in a forward direction. The torque of each coil depending upon the fixed coil current. Okay, so if there is a discussion of equalizing both of the terms at an equilibrium position, if we equalize T suffix A is equal to T suffix B, what will happen at this inception? If T suffix A is equal to T suffix B, the deflection of the instrument, entire deflection of the instrument is measured with respect to phase angle of the circuit. That means it may be noted that it may be most important note what we can say, that means instrument must be designed and it should be calibrated at a common constant frequency. At what particular frequency we are going to use, we have to design the power factor at that frequency only. In case if this single phase electrodynamometer type power factor meter is designed for any other frequency, okay, let us assume if we design this frequency for, if we design this meter for 50 hertz, if we design the frequency meter, if we design this power factor meter for 50 hertz, and if we operate the power factor meter other than 50 hertz, okay, that will create a frequency harmonics in the line, and this will impact the entire frequency deviation of the line. Okay, so that's why we equalized both of the torque conditions here. Okay, is it clear? Okay, is it understandable? So the next discussion of further classification, what we are going to discuss, that is three-phase electrodynamometer type power factor meter. So previous discussion we discussed about single-phase electrodynamometer type power factor meter. Now we are discussing about single-phase electrodynamometer type power factor meter. Okay, so the construction is quite similar to the single phase, but here there is a difference, that is moving coils are displaced at a particular dimension of 120 degrees. Previously that is 90 degrees, here it is a small mistake, it is deviated with respect to 120 degrees. Okay, if we see the construction here, if we observe the construction of this electrodynamometer type power factor meter, it is used for an balanced load in entire discussion, even in the measurement of power in three phase 4-wire system, even in the measurement of power in three phase 3-wire system, either it is a 1 watt meter method or it is 2 watt meter method, either it is 3 watt meter meter. In a, and always the theoretical discussion is quite limited with respect to balanced load scenario. Balanced load scenario, here also we were discussing three phase power factor meter for balanced load. In a balanced load, in a balanced load, at a particular balanced load, the phase angle distribution between three phases is always 120 degrees, always 120 degrees. So three phase power factor meter, the readings should be shown in an accurate manner when the load is in balanced condition. So if you observe the instrument contains two moving coils and a fixed coil which are at a distribution of 120 degrees apart. Okay, so the connections are across two different phases of the circuit. See, the connections is mostly limited with respect to two phases of the circuit, but the third phase is connected to current. The main purpose of third phase, see here, in the main purpose of third phase is to carry the current flowing through the line. The current flowing or the current carrying of the entire system is observed with respect to third phase. Initially there is no necessity of splitting the phases, but there is a requirement of phase displacement between moving coils. There is a phase displacement with respect to the moving coils at a particular angle theta. That's why we displaced the phase. Okay, two moving coils, coil A and coil B of pressure coil is displaced at a particular dimension of 120 degrees apart. Okay, the angle through the pointer is deflected with an unity power factor condition and it is equal to the phase angle of the circuit. Okay, the entire three phase instrument, in this entire three phase instrument, it is independent of frequency. Since the current coil, since the current is carrying with respect to two moving coils and it is affected is the same way with respect to the change of frequency. So if we observe the working analysis, this is about the peculiar construction. People say this is about the peculiar construction. If we see the peculiar construction perspective, same, the peculiar construction is different. Same, fixed coil will carry the currents. That's why it is fixed coil is called as current element, and the this particular moving coil will carry certain amount of voltage. That's why it is called as voltage element. Current flowing through this fixed coil will create a magnetic field, and this coil A will create a deflection torque and coil B will create a deflection torque. Both are in opposite direction. Coil A will have a resistance, high resistance circuit. This is a non-inductive resistance. Coil B will have inductive element. Sorry, coil B is also having high inductive elements. So if this is about the peculiar construction, so the needle is connected on a particular axis scale, which is pivoted here. So if we go on through the working inception, the field is created with respect to the fixed coil. Okay, the voltage flowing through the coil A is V12 and current flowing is nothing but IA1, and voltage flowing through the coil B is represented with respect to V13 and current flowing through is IB1. Both are having a phase displacement of 120 degrees. So if we see the phasor analysis, of this particular three phase electrodynamometer type power factor meter, if we observe the phasor analysis, the phasor analysis clearly describes about the behavior of voltage and current. Okay, in this complete phasor analysis, what we are going to see means, okay, the behavior of V1. See, so this is the value, that is V1, this is V2, and this is V3. V1, V2, V3 are displaced at a particular dimension of 120 degrees apart. 120 degrees. The phase displacement between V1, V2, V2, V3 and V1, V3, that is 120 degrees. Okay, if we substitute, if we reflect the value of V2 in an opposite direction, that is represented as minus V2. If we represent the value of V3 in opposite direction, that is represented as minus V3. Okay, and the exact phase angle between voltage and current, see, the phase angle between voltage and current is represented with respect to 30 degrees. Okay, V1 and IB phase angle is around 30 degrees, V1 and IA phase angle is around 30 degrees, 30 degrees. Okay, so how to represent the behavior of currents here, how to represent the behavior of currents here? Okay, the phase angle between V1 and IA and the phase angle between V1 and IB is represented as 30 degrees, but at what particular instant that current is lying? Okay, IB is in phase with respect to V13. That is an important point. IB is in phase with respect to V13 because V13 is the current flowing. At what particular instant V13 is the current flowing? V13 is the current flowing with respect to coil B of moving coil. Coil B of moving coil, or coil B of the particular plane B of moving coil. IA is nothing but current flowing through the IA is nothing but current flowing through the moving coil. Okay, IA is nothing but current flowing through the plane A of moving coil, where the voltage produced is V12. That means V12 is in phase with respect to IA and V13 is in phase with respect to IB. Okay, so that is about the phasor analysis. If we analyze the phasor analysis with respect to the torque expression, torque produced by the coil A, that is equal to T suffix A is equal to K into V, K into V I12 maximum mutual inductance M max, that is equal to cos of 30 plus 5 into sine of 60 plus 5. Okay, so T suffix A, that is equal to root 3 into K into V into I12 into M max cos of 30 plus 5 into sine of 60 plus 5. Torque produced by coil B, that is T suffix B is equal to K into V into I12 M max to cos of 30 minus 5 to sine of 120 plus 0 degrees. T suffix B is equal to K into V into I12 into M max cos of 30 minus 5 into sine of 120 plus 5. That means if we substitute these values, if we equalize the values of torque produced by the coil A and torque produced by the coil B, if we equalize these particular parameters, that means torque produced by the coil A, and if we equalize both of the parameters, torque produced by the coil A and torque produced by the coil B is equalized. Okay, so that means the instrument of two moving coils are fixed with a particular phase displacement of 120 degrees. Okay, and are connected with the two different phases of supply current, right? So, and we are equalizing two particular torque with respect to coil A and torque with respect to the coil B. So at that instant, the fixed coils are connected with respect to the third phase and they carry with respect to the line current. That means there is no phase displacement between the currents here. So even we said that the moving coil is having a phase displacement of 120 degrees. This three-phase instrument will give an indication with respect to frequency at a particular uniform structure. At a particular uniform structure, since the current is flowing with respect to the two moving coils, and it is also affected with respect to the same as the frequency changes with respect to the distribution, so this dynamometer type wattmeter, three-phase dynamometer type wattmeter is more accurate when compared to the other classifications, but there are certain limitations here. Most important limitation here, that is the limited range of scale. The scale range is quite limited here. And the connected ligaments of threads of the particular moving coils are adjustably required, and they are minimally restrained, and in order to accomplish the particular degree of deflection, we need a certain additional deflection torque. We need a particular additional deflection torque. So here we equalize the torque expressions, and what we analyzed with respect to the additional parameter, at the end of the discussion, the deflection torque of the coil is always directly proportional to the angle which is suspended in between two moving coils. Angle is suspended in between two moving coils. Between two moving coils. So up to now, one second. So up to now we discussed about the definition of power factor and what is the requirement of power factor meter. Okay, at what particular instant we use a power factor meter? The main purpose of power factor meter is to measure power factor on a particular transmission line. Okay, what is power factor? Power factor is a cosine of angle between voltage and current. It will give us about the angular discrimination, the angular distribution or displacement between voltage and current. Okay, so the power factor determines the types of loads which we are using in an industrial load or domestic load or in whatever it may be the type of load. Next, we classified about the power factor meters into various types. Okay, electrodynamometer type power factor meters, single phase electrodynamometer type power factor meters, and three phase electrodynamometer type power factor meters. Next, we discussed about the construction of electrodynamometer type power factor meter. Okay, we analyzed the construction with an independent perspective. We discussed about the construction of fixed coils and how the flux is distributed, and we discussed about the behavior of moving coils on a particular calibrated scale. And next we analyzed the torque expression. Okay, and next we also discussed about three phase electrodynamometer type power factor meter. We analyzed the construction and we also discussed about theoretical working. Okay, and next we discussed about the phasor diagram analysis. Individual phasor diagram analysis. So in next coming classes, we will discuss about moving iron type power factor meters.